Okay, we got another one. Alright, now the first thing I wanted to tell you guys was one thing that, I'm a structures person, and the one thing I noticed when I took the PE was that all the questions are relatively easy, but the problem is, do you have all the right reference material? Do you know what the cross-sectional areas are for all the bars, etc., for pre-stressing rods? Do you know the strength of nails, etc., things like that? Alright, so the biggest thing that we need to do is you have to know where all your material's at. All your reference sources, you have to try and get that organized before you go and take this exam. Because if you try and do it during the exam, you're going to get killed because you're not going to have enough time. The second thing I wanted to warn you about were these notes themselves. I just developed them. I went through them a million times, and hopefully there won't be many errors. There are a few that I've noticed, and I'll tell you about them as we go through, but I haven't found too many. They're fairly complete. It's a decent set of notes. It's a lot of how-to-do procedures. In other words, if you want to design a beam, it gives you the steps to design the beam. Alright, I tried to make the notes so that if you went in and took this exam, you can go ahead and jump into these flow charts and actually go ahead and design it really quick. We also have codes. You have to get used to the codes, and the first one that I guess you see here is the code for reinforced concrete. It's the 31889. If you're going to take this exam, you've got to bring this book if you plan on doing a concrete problem, because they're going to ask you to design it according to this spec, and there's going to be a lot of things like spacing of stirrups that maybe you don't recall off the top of your head, or but this would be a good book. Any code, really, even if it's the LRFD, or you have to bring those things in with you to class. All right, now
Joe.
Yeah,
Joe. I started looking at this chapter 14 of the book here.
Right.
This Lundeberg.
Right.
And a fair amount of those numbers are outlined in his chapter 14.
Yeah, that's true.
How do you advise? I guess one of the things I'm kind of worried about is you end up bringing in so much stuff that you can't wade through it in time.
That's exactly.
Is a chapter, something like chapter 14, give you enough information for tables and things like that, or you're saying no?
I believe it is. My notes were developed off of that book, sort of. What I've done was I've taken the class notes that I use here at Texas A&M, and then I compared it to what the book said in chapter 14. And we more or less go along the same lines. And as I was looking into that chapter 14, it's relatively complete with all the ACI references and things like that. It has all the areas of steel for the rebars and the different things for the modulus of elasticity, etc. So yeah, it's pretty complete. You can pretty much go by that. All right, I'd say that's probably enough for you.
Okay.
Okay, the second one, which is not in Lindbergh book, is the masonry code. All right, and the only recommendation I'm going to give you with masonry, how many of you have ever designed anything with masonry or have used masonry? That's pretty much what I thought. Skip this problem if you see it, because there's a lot of details in these codes that if you're not familiar with it, even though the problem may be easy structurally, just the fine details are going to create problems. Okay? So I'd recommend to you to try and avoid this. I have a brief summary in the back part of these notes into masonry structures, though, just in case someone was interested in doing this problem. Okay, the demands. All right, I'm going to present pretty much everything today is going to be based on capacity. I'm going to tell you how to design a beam, how to find the beam's capacity, a column's capacity, etc. Dr. Lowry in the last two lectures told you how to find demands. And in any problem that you get on this PE exam, they're not going to tell you, all right, design this simply supported beam where a moment is equal to 100 kip feet. That's not going to happen. They're going to give you the beam and they're going to say there's a load on it, and you're going to have to use statics to try and solve for the shear diagram, the moment diagram, and then you're going to go design the beam. Okay? So just get that put into your brain, because the biggest part of these problems is going to be the statics. All right? Especially in the when they give you the sections when you have like 10 questions that are all part of the same one. All right, there may be part of it's going to be related to the statics, part of it's going to be towards the design of the concrete. Okay? There's also a lot of good example problems in the Lindbergh book. All right, he has a sample solution exam. He has the problems and the solution, and then he also has another book on the example problems, and there's a lot of nice problems in reinforced concrete there. If you can do those problems, I think you're ready for the concrete part of this exam. Okay, so what I would recommend is you take a good look at these notes, then go into these example problems, see what he did, make sure you know how to do those, and you should be ready for the exam. Okay, we'll try and get right into it. First of all is in the mixing of the concrete. And there's all different types of cement. Basically it's called Portland cement, and it's a mixture of Portland cement, sand, aggregates, and water, and all other types of additives, which creates a mix called concrete. All right, now there's all different types of Portland cement. Type 1 is normal cement. Okay, and it's basically what you see in probably 90% of the construction. It's general purpose type cement. The second one is a modified Portland cement, which has moderate sulfate resistance and is used in hot weather for large structures. Type 3 is an early strength type of cement, so it'll give you 28-day strength in 7 days. Type 4 is a low heat of hydration, and they use these in dams and things like that. And type 5 is for a very corrosive type environment where it's sulfate resisting. Now, how do you proportion concrete? Well, normally it's designated as a ratio of cement to fine aggregate to coarse aggregate. Again, the fine aggregate is going to be your sand, the coarse aggregate is going to be your stones. Okay, typically this ratio is something like 1 to 2 to 3, something like that. The ratios can be in terms of weight or in terms of volume. Just a couple of number quantities here. The amount of water is usually quantified in terms of gallons of water per 94-pound bag of concrete. Or another way they do it is called the water to cement ratio. Now the in-place volume method, or the absolute volume method, is a way of determining how much concrete you're going to produce when you mix all this stuff together. And basically it's the sum of all the solid volumes of cement, sand, coarse aggregates, and water, and any voids that you have. Alright, so if you have something where you know you need to create 1 cubic yard, well, you have to make sure when you put all this stuff together you're going to get 1 cubic yard. Some of the typical specific weights for cement, it's about 195 pounds per cubic foot. The fine aggregates, it's in the neighborhood of 165. Coarse aggregates, it's the same. And water is 62.4. One cement sack is about 94 pounds. Pretty much referenced with respect to this 94 pounds. And you'll see an example problem later as I show you. 7.48 gallons is 1 cubic foot volume. Okay? We talked a little bit about air entrainment, or voids. You put some voids in the concrete for a lot of different reasons, temperature, etc. When you put voids into the concrete, what it's going to do is it's going to increase the volume of your concrete. So basically what we're going to do is we're going to increase the yield by additional air. And what you do is you divide the yield that you expect in your concrete by 1 minus the percentage of air, okay, which is going to give you a bigger quantity. The water content in the aggregates above saturated surface dry must be subtracted from the total water required. Now, just imagine sand. If it's sitting out in a field and it's raining like crazy, okay, that sand is going to be drenched. It's going to be soaking wet. Well, you have to figure out how much additional water is in that sand when you put it into the mix, and then you need to subtract that off the water that's required from the mix. Same thing goes with a stone, and if it's below, if it's very dry, then you need to add additional water. Okay, the density should be saturated surface dry. Okay, and normally that's specified by the manufacturer, by the batch producer. So here's a quick example. Alright, a mix is designed such that the ratio between the cement to sand to stone is 1 to 1.9 to 2.8 by weight. The water to cement the water-cement ratio is 7 gallons of water per sack of cement. So what we want to know is what's the concrete yield in cubic feet per sack of cement, and how much of each constituent is needed to make 45 cubic feet or 45 cubic yards of concrete. All right, now typically what you're going to do is you're going to set yourself up a little table here. That's all this is a little mathematical trick. You watch your units, and then you can back calculate and figure out what your yield is. Now, if you know that your materials are cement, sand, and aggregate, all right, and you have your water down here at the bottom, I already told you that the ratio was 1 to 1.9 to 1.8. Okay, and if you talk about the weight per sack of cement, right, we know the cement weighs 94 pounds per sack, so you multiply your ratios by 94, and what you're going to come up with is 94, 179, and 263, and that's pounds per sack. Okay? Now the solid density of each material is in pounds per cubic foot. All right, now just take a look. If you divide your first column by the second, what you're going to get is the amount of volume. Just watch your units. The pounds cancel, and what you're left with is cubic feet per sack. If you add the three terms up, plus the part required for the water, which is 7 gallons of water per bag of cement, and I already told you before that 7.48 gallons of water is 1 cubic foot volume of water. So if these are your volumes, if you add them all up, what you get is 4.1 cubic feet of concrete per sack of cement. Okay? So the number of sacks that you need can be found from this formula. We know we need 45 cubic yards, and 27 cubic foot is 1 cubic yard. And if you divide this now by the total yield that we found from before, again, you watch your units, everything cancels out, you're left with 296 sacks. Or we can say 297. Okay? So how much of each material do you need to order? Well, it's the 297 bags times its ratio. Okay, so if you go back to that first sheet, the cement had a ratio of 1. Okay? The sand was 1.9 times the 94. And the aggregate was 2.8 times the 94. Alright, this gives us 26.5 and 39.1. And you can figure out your total gallons of water. It turns out to be a little over 2,000. Okay? So basically, you just watch your units with these types of problems. Second example is 50 cubic feet of 1 to 2.5 to 4 by weight of concrete are to be produced. The constituents have the following properties. Cement, we know, is 197 pounds per cubic foot. That's the saturated surface dry density. Okay? The sand has 164 and the coarse aggregate has 168. Now, the moisture is also given for each of these specimens. So the sand, we said, has a 5% excess of water above the saturated surface dry weight, and the coarse aggregate has a 2% deficit. So what's the required order quantities if the design calls for 5.5 gallons of water per sack and 6% air entrainment? Remember, I said before, air entrainment creates voids, and what we're going to do is we're going to increase the yield by 1 minus this percentage. Okay, and you'll see that on the next sheet. Okay, so again, set yourself up a little table here. You got cement, sand, your coarse aggregate, and your water. The ratios are 1 to 2.5 to 4. The weight per sack we know is 94, 235, and 396. Okay, saturated surface dry you find from the previous table, and if you divide this the third column here by the fourth, what you're going to get is the amount of volume, and when you add it all up, you're going to get your total yield. This turns out to be 4.883 cubic feet per sack. Okay, and again, because we're adding air to it, we're going to increase that yield. So we divide by 1 minus 0.06, and you see you come up with about 5.2 cubic feet per sack. Okay? Now, if you need to make 50 cubic feet, what you need to do is divide your 50 cubic feet by the amount of yield based on 1 bag of cement. This gives you 9.63. So typically we would say, all right, let's use 10 bags of cement. Okay? Well, in this problem, they just used the 9.63, but you multiply your 9.63 for finding the required amount of sand. It's the 9.63 times 1.05. Now, the reason the 1.05 comes is because the sand has a 5% excess of water. Okay, so the amount of sand that you're getting is actually a little less. That's why you have to use 1.05 here. Okay, times the 94, which is with the weight of the sack, times 2.5 is based on the ratio between cement to sand. Divide by 2,000 to get you into tons. It turns out to be 1.19 tons. Same thing goes for the coarse aggregate, except this time we have a 2% deficit of water, and that's where the 0.98 comes from. Okay, this gives us 1.77 tons. The excess water in the sand you can calculate from this formula. It's the 1.19 tons from up here. That's the amount of sand that you're using. You have a 5% excess. Divided by your 1.05, that's basically just like a ratio. It's the amount of water as compared to the amount of sand. Times your 239.7. And I'm trying to think of where that comes from. That's gallons per ton.
How many gallons per ton of water? The ratio.
2.3.
This here. 239.7 is a constant.
Okay, that's probably the weight per ton, right? Okay, so it's the amount of volume per unit of weight. Okay, that could be. All right, and that turns out to be your 13.58 gallons. Okay, and the same thing goes for the aggregate. You can figure that out. It's basically the same formula with the same constant. This turns out to be an abscess of 8.66 gallons. So your total water requirements are the parts required for the mix, plus the additional part from the sand, which was the 8.66. And we know that the stone had an insufficient amount, and we needed to add on an additional 13.58. This gives us a total weight or total volume of water of 48 gallons. Okay? These types of problems are basically watching your units.
So would you subtract that excess water from the sand, the 13.58? Okay, so you got it.
I'm sorry, I think I said that wrong. The 13.58 was from the sand. Right? That's the additional part from the sand. The 8.66 is below the saturated surface drive for the stone. So when you figure out your total volume of water, it's the part required for the mix, plus the additional part that you need to add in for the stone, minus the excess from the sand. Okay, I think I said it right that time.
I wasn't turning my pages quick enough.
Okay? Now, some of the properties of concrete. First of all, we have a slump test, and what that is that's a measure of concrete plasticity, how easy the concrete's going to flow. And typically when we do this test, it's going to be in the area between 1 inch and 4 inch. If it's less than 1 inch, it's going to be a very stiff mix. It's hard to pour. If it exceeds 4 inch, the water to cement ratio is going to be very high, and the strength of the concrete is going to go way down. Okay, so typically we like to stay between 1 and 4. The compressive strength in concrete is typically found from cylinder test, and for normal concrete it can vary anywhere between 2 and 8 KSI. And nowadays we have this high strength concrete, and that can vary anywhere between 8 KSI and to as high as 25 KSI. Okay, I know in Chicago they're actually building with 16 KSI concrete in a lot of their skyscraper buildings right now. The tensile strength in concrete is typically about 7 to 10% of FC prime. Concrete, we know, is very strong in compression, very weak in tension, and you can see that here. We find the tensile strength either from a split test or a rupture test. And if we do the rupture test, ACI has come up with a conservative strength value of 7.5 root FC prime. Okay, where FC prime is in PSI. And I'll be bringing this term up a little later in the lecture. The shear strength is a little greater than the tensile, but still significantly less than the compressive strength. It's about 16 to 25% of FC prime. And ACI in section 11.3.1.1 says that the capacity of concrete in shear is 2 root FC prime times B times D. The density for normal reinforced concrete is about 150 pounds per cubic foot. For lightweight concrete, it's about 120 pounds per cubic foot. The modulus of elasticity, the code in ACI says to use either one of these two equations. 57,000 root FC prime is sort of an easier one to use because you don't have to worry about this exponent. And typically this is about 3,600 KSI if your FC prime is about 4,000.
Quick question, what's ACI stand for?
It's the American Concrete Institute. Okay, and the first code that I showed you for reinforced concrete is called Building Code Requirements for Reinforced Concrete, and that's an ACI 318-89. Okay, so when I put a reference ACI with the number, that's corresponding to a certain section in this code. Okay? Lindbergh book also has these things too. Alright, now as far as the stress strain behavior for concrete, if you're doing a cylinder test where it's
Joe?
not, yes.
Before you leave that, what are they doing different to come up with this high strength concrete? What's done differently in the process to come up with that?
Number one is the water to cement ratio. As I said before, the higher that ratio is, okay, the weaker the strength's going to be. So what they try and do is they try and find a concrete mix with a very low water to cement ratio. And what they're doing now is they're using different types of additives. Okay, one thing that you can use is super plasticizer, and what that does is it releases some of the water in the sand, okay, so that you do not have to add additional water. Okay, that's one thing to get higher strength. Another thing is that they have all these different additives like, the names aren't coming to me right now.
Don't look at me.
Silica fume, there's one of them definitely is silica fume, but there's others out there. Down in Texas, I know there's a building in Texas down in Houston that I think was designed with lightweight concrete and an FC prime value of close to 12 KSI. And I think at the time it was the tallest concrete structure that was built with lightweight cement. As far as the other aggregates go, like I said, I can't recall them off the top of my head, but I know one of them is silica fume.
All right.
Alright, now as far as the stress strain behavior goes, for concrete we know it's very brittle if it's unreinforced. And typically what happens is that as you load your specimen in compression, it begins to deviate off the linear line at about 30% of FC prime, and you get this nonlinear behavior up to its peak strength, which we call FC prime. It begins to degrade, and that number then becomes 0.85 FC prime at a strain of about 0.003. Okay, this is how the current code is based, and this is based on unconfined concrete. Now, just think about if you take this cylinder and you try and confine it laterally. What's going to happen is that the cement mix that you get can have a lot more strength. That's a value that's referred to as F sub CC prime, and that increase in strength can go up, from 20% to maybe as much as 50 to 75%. The other big thing to note is that when it's unconfined, this point drastically fails very fast. It's very brittle. If you confine it, this level of strain can go out to a very large range, which means it's more ductile. And for earthquake zones and when you're dealing with blast loads and things like that, you would always want your sections confined just based on this property alone. Okay, it's increased ductility. I'm not going to talk much about that.
Could you give an example of the difference between confined and unconfined concrete?
Okay. If you have your cylinder, okay, what we're going to do is we're going to put a compressive load on it. If you just go ahead and load this thing until it fails, we're going to get that lower bound curve. Just imagine if you came here and you put some straps all the way around the cylinder now. Okay, and then you load this guy up. What's going to happen is that failure plane right? The way the cylinder is going to fail is sort of like this. Okay, it'll split on a diagonal fashion, close to 45 degrees. All right, now if you come in here with these straps to try and prevent that crack, I think it's obvious that the strength is going to go up. Do you see that?
Mm-hmm.
And if you make these bands of a very ductile material like steel, what happens if these bars begin to yield? Then you can think about that yield deformation. It's going to continue to go on. It's going to be a much more ductile section. Okay, so that's really what confinement is. And these are important for column members, for bridge-type structures. You think about your piers. And all these earthquakes, whenever a bridge falls down, it's pretty much at the pier. And if you look, it collapses right below the slab deck or right above the footing, okay, because that's the maximum stress zone. Part of the reason is because it fails in shear, like this type of mechanism, okay. One way to avoid that is to put in additional straps, okay, to avoid that failure mechanism. Okay? So what we're doing is,
Thank you.
the original situation may have performed like this, where once you got to this level of force, the strength degraded really fast. Okay? But during an earthquake, you really don't know what the level of force is. So what if it hits its peak? The only thing we want to do is to make sure that it can take additional deformation. And you see when a specimen is confined, it could take that additional deformation. Deformation corresponds to strain. Okay? Same thing goes in a blast type load, or hurricane, or any other type of catastrophic load. I doubt if you'd be asked that in the PE though. Now, rebar, I think everybody knows what its characteristics are. Again, stress versus strain. If you have a grade 40 bar, it's going to load up basically along a linear line. That stiffness, E, is about 29,000 KSI. Once it hits its yield strength, there's what's called a yield plateau, and then there's a slight increase in strength. That's called strain hardening, until it reaches its maximum value, and then finally fails at its fracture strength. Okay, the only one that we're really concerned about is its yield strength, because that's the one we're going to design with. The difference between grade 40 and grade 60 steel, number one, is the increase in strength. And number two, you'll notice that the grade 60 steel did not go as far in strain or deformation. And the reason is because it's a little bit more brittle. Okay, but still you have considerable amount of ductility even in the grade 60 steel. When you start getting up to 120 grade steel, those things will load up, hit its peak strength, and then come down and collapse right here. So you can see it's very little ductility. Okay, and a lot of pre-stressing tendons have this type of characteristic. So what you do for this case is just make sure that your demands are always in here and you don't have anything to worry about. For rebar, if it hits its yield strength, so what? You still got all this deformation capacity back here. Okay, this comes from Limburg, and these are your rebar properties with all the different sizes. One thing that I can tell you about the diameter is if you take the bar size and divide it by 8, that's going to be the diameter. So a number 6 bar, 6 divided by 8 is 3/4. Okay, cross-sectional area is just pi d squared over 4. And that gives you this number here. The perimeter is just 2 pi r, or pi times d. Those numbers are all quantified for you. I'm also going to leave you a little note here. It's on page 14-12 of the Limburg book. And I believe what this thing does is it has all the different sizes of bars plus the number of bars quantified. So if you have an area of steel required of, say, 6 inches squared, you can look up into that table and try and figure out what's the best combination of bars to use to match that 6 inches squared. Okay, so that's a handy table too. Is that true?
Well, yeah, that number, that 8/8 bar, 7/8 bar, 6/8 bar, past number 8 bar now, that doesn't work. For instance, you look at number 10 bar, doesn't have 10/8 for the diameter, does it?
It's close.
Yeah.
It's close, but it's not exact. I think it's a good approximation.
But anyway, you got all the numbers.
You
right
got the
there.
tables in front of you.
Right, and you don't want to do pi d squared over 4 anyway. You just want to pull it right out of the table.
All right, now, as far as concrete goes, it's ultimate strength design. Okay, there's no allowable stress design. I guess you guys are accustomed to that because you're using LRFD. What we're going to do is we're going to take the actual loads and we're going to multiply them by what's called the load factor. Okay? And then we're going to compare that with loads that cause failure. Okay? We're going to try and find out what's the maximum that you can actually take the structure out to. That's how we're going to design it. And then we're going to check it for service type loading, so for deformations and things like that. Okay? And I know a lot of times you'll be walking in a building and you'll find out that as you walk across the floor you start bouncing around. Those are serviceability problems, not ultimate strength type problems. What we're worried about are earthquakes and things like that. Or if you just came into a room and just fully loaded it up with all the live load and dead load that you possibly can. You just want to make sure it doesn't collapse under that scenario. Ultimate strength is multiplied by what's called a capacity reduction factor. Sometimes it's called an undercapacity factor, and this thing is defined as being phi. And what this does is, it's typically been referred to as a dummy factor, and it accounts for workmanship and material understrains and things like that. So basically your equation is going to be phi times m sub n, which is the nominal capacity. It's equal to the summation of all your alphas times your certain moments. Okay? So you'll have a certain load factor for dead load, plus a certain load factor for live load. And on the next sheet, actually I quantify the phis first. If you're dealing in flexure, if you have a beam and you're dealing in bending, the phi is 0.9. If it's an axial tension member, it's 0.9. Shear and torsion is 0.85. Axial compression with spirals, it's 0.75. Compression with ties is 0.7. Bearing is 0.7. And unreinforced is 0.65. The reason it's going down is because of the uncertainty. Okay, just think about unreinforced as compared to flexure. It's a lot easier to find a flexural strength than it is to find an unreinforced strength. Okay, so that's why that factor goes down the whole way. This is an ACI 9.3. Now, again, go ahead.
What's a spiral?
Okay. If you're in a column,
confined concrete.
if you're in a column, and let's say your column is square. Okay, typically you'll have bars in the corner. And what you're going to do is you're going to provide what's called a hoop or a stirrup around these bars. Okay? This is referred to as a tie. Now, if you're in a circular column, where your longitudinal bars now are going to be spaced around the diameter, what you're going to do is you're going to put this stirrup in, which does something like this. And if you look in elevation, okay, well, these are your bars. Okay, what it's going to be is it's going to be some type of spiral that goes all the way around. Okay, something like that. You understand that?
Yes, thank you.
Okay, where in cross-section for this guy, it's going to look like this. Okay, as far as confinement goes, this guy is much better. Okay, and I think if you look inside the core here, as compared to this corner here, what happens in the corners is that you have some discontinuity, okay, and you lose some confinement based on the corners, where if it's in a circle, it's a lot easier to confine something. Okay, just imagine wrapping your hands around something that's circular and then something that's square or rectangular. It's a lot harder to get your hands around it. So the effectiveness of the confinement is better for a spiral.
Thank you.
Okay. Alright. Now, we went through the phis. As far as the load factors go, it depends on what you're looking for. If you're designing for dead load and live load only, then there's only one combination to check. The ultimate demand, U, is equal to 1.4 times the dead load plus 1.7 times the live load. Okay, this is quantified in section 9.2 of the code. If you have to deal with wind, alright, there's two additional equations that develop. You get 75% of 1.4 dead plus 1.7 live plus 1.7 of wind, and 0.9 dead plus 1.3 wind. So if you're designing a building for dead load, live load, and wind load, you need to check all three of these load combinations. Now, what do I mean check? You need to find shear and bending moment diagrams for each of these cases and develop what's called a moment envelope. Put all of these demands together, and whichever gives you the biggest moment, that's the one you design for. Okay? If you have earthquakes, then that comes in here. There's also other types of loadings, temperature, etc., things like that. They're also quantified in 9.2. I think pretty much for this exam, you'll only be governed with the first one. Okay, I hate to commit to that, but I think realistically, when they start asking for wind load, that's horizontal loads, and the problems could get a lot more difficult. Okay? Alright, so now we get into bending. Alright? Assumptions, right off the bat. Plane sections remain plane. And if you don't know what that means, what that's saying is that the strain diagram is linear. So in other words, there's no slip across the cross-section of a member when it bends. Okay, there's a perfect bond between the rebar and the concrete. The stress in the concrete is proportional to the strain. Okay, this is Hooke's law. When the stresses are below cracking. This is elastic. Now, when the stresses in the concrete in tension exceed its cracking strain, the concrete is basically gone. There's nothing there. So what we do is we neglect it. We only consider the concrete in compression when we're beyond the cracking strain. Okay, and this is important for ultimate strength. The criteria number 3 here is important when we're considering service loads, when we talk about deflections. Okay, the loading stages, there's 3 of them. Initially you have this beam, there's no load on it. So is any part of the concrete cracked? Well, probably not. Alright, so if you start to put a load on this beam, what's going to happen is that the concrete is going to continue to load, but it's still in the elastic region. Okay, it'll stay elastic up to its cracking strength. Alright, and that cracking strength I define to be M crack. Now, once it exceeds this value, what's happening is that the concrete cracks, the stiffness of the beam changes. Alright, and that's going to basically load up along one linear line up to its yield strength. And that's when the rebar at the bottom begins to yield. It'll continue past this point up to its ultimate strength. Okay, now I'm going to carry you through these 3 load stages. The one that's important for flexure is this one. The one that's important for deflections is this one. Okay, because there's an equation where you have to find M crack and M ultimate. Okay, and I'll show you that later. Now, if your section's uncracked, then it's just like dealing with any other thing. If it's steel or any other section where you have a full cross-sectional area. This whole area of concrete acts within your section. Okay? Your strain diagram I told you before was linear. The stress diagram, because we're below cracking, we're at uncracked stage, the stress diagram is also linear. So what's saying is that you have a compression force in the concrete, that's C sub C. You have a tension force in the concrete, that's T sub C. And there's also a tensile force in the steel, that's T sub S. Well, how do we find this cracking moment? Well, you find that from strength of materials. We already know that the bending stress is My over I. Okay? And typically what we do to find the cracking strength is that we substitute for the stress F sub R, which is the rupture modulus. That's on the next sheet. So rupture modulus times I gross divided by Y sub B, where Y sub B is the distance from the neutral axis to the extreme tension fiber. F sub R is the allowable stress. So in other words, once you exceed that stress, the concrete cracks. Alright? So that's how we're going to determine our bending moment. Now, once we exceed that crack capacity, okay, what's going to happen is that the concrete at the bottom is going to begin to crack. Alright? The cracks are going to develop vertically. Okay, and that's why I got those dotted lines in there. Those things are cracks. Alright? Now, above the neutral axis is where your concrete's acting in compression. Alright, you have your area steel down here at the bottom. It's at a distance of D from the top. The distance to your neutral axis is what I define to be as X. The height is 8, the width is B. Okay? So because the neutral axis hit this point, we had cracking, the strain diagram looks like this. Okay? Where we know this strain exceeds the cracking strain in concrete. The stress diagram is going to look something like this in compression, but notice there's nothing here at the bottom. Again, because the concrete crack is no longer acting. The only thing that's acting on the bottom is the steel. Okay, so you have your stress in the steel, F sub S. So what we're going to do to find this, the moment now, is we have our stress distribution in the concrete in tension. This is a triangle, and what we're going to do is we're going to relate this stress back to a force, C sub C. We know the tension force here in the steel, and we have this moment arm, JD. Okay? And once we know JD and we know either C or T, we can find its moment, its yield moment. All right, now here's how we're going to do this. Number one is equilibrium. This section is not moving, so sum of forces must equal 0 horizontally. So C sub C has to equal T. Okay, C sub C has to equal T. All right, C sub C is the stress at this point, which is FC prime, times the area of the triangle. Okay, the area of the triangle is the base, which is this width, times the height, which is x, and because it's a triangle, we have to divide by 2. The area of a triangle is 1/2 base times height. So you take your stress and you multiply that by the area in compression of concrete. So that's F sub C Bx divided by 2. T is just equal to the area of steel times the stress in the steel. The stress in the steel we know is F sub S. Okay? So what we're going to do is solve for F sub S. F sub S is equal to F sub C B times X divided by 2 times the area of steel. Okay, is everybody with me up to here? Okay. The next law is what's called compatibility. And just take a look here. You have a linear diagram, right? Well, we're going to use is similar triangles. All right, if I say that the strain in the layer of steel, that's epsilon sub S, right? The strain in that layer of steel divided by the distance from the neutral axis down to that rebar is a distance of d minus x. So you have the strain in the steel divided by d minus x is equal to the strain in the concrete divided by x. Okay? Now, the third law is what's called Hooke's law, or the constitutive law. And that's when we know that the stress is equal to the modulus times the strain. Okay, so we know the stress in the steel is equal to the modulus times the strain in the steel. The stress in the concrete is the modulus times the strain in the concrete. Now, if you substitute these strains into here, and then plug those back into your first equation, what you get is this equation on highlight 4. You get x squared is equal to 2 times n, where n, I guess I don't have that here, n is the E of the steel divided by the E of the concrete. Okay? So you got x squared plus 2n times a sub s times x divided by b minus 2n a sub s d divided by b. Okay, if you take a look in this expression, the only thing you won't know in this section is x. Okay? Rho is equal to the area of steel divided by BD, that's the reinforcement ratio. And what I'm going to do is I'm going to define another term, which I'm going to call KCR, or K crack. And that's equal to x divided by d. Alright? Now if I plug these two equations back up into here, what I get is one expression for K. And that's equal to the square root of rho n squared plus 2 rho n minus rho times n. Okay? Now, once I know this K, I can find back my x. Alright, I already told you before that K was equal to x divided by d. So I can back calculate and find now x. It's just K crack times d. And I crack is just equal to what now? Well, let me go back to that first sheet. What's the moment of inertia of this section? Well, you have the concrete in compression and then you have your steel here at the bottom. Well, what's its moment of inertia about the neutral axis? Well, it's 1/12 the base times the height cubed plus the area of the concrete, which is base times x over 2. Okay? Or, that's the same thing as saying that it's 1/3 bx cubed. Okay, there's two different ways of doing that. Probably the easier thing is just to use this equation. It's just bx cubed divided by 3. And then you have the part from the steel, and that's just the area of steel times n to get an equivalent section, times d minus x squared. D minus x is the moment arm from the neutral axis to the area of steel. Alright?
I have a question.
Okay.
I understand where you came up with that, but you made a statement about your inertia being equal to 1.
This guy here, you mean?
Okay.
Yeah, the moment of inertia of a rectangle about its base is bh cubed over 3. That takes into account the bh cubed over 12 about the centroid plus the AD squared. You add all those terms together, moment of inertia of a rectangle about its base is BH cubed over 3, and that's where we want that concrete part. Then you got to add the AD squared for the steel.
All right, there's two ways of doing it. Okay, if you got a rectangle, and here's the axes that I want to take my moment of inertia about. Okay, the moment of inertia of this rectangle about its own centroid is 1/12 BH cubed. Okay, what is the parallel axis theorem? It says that you have to add on AD squared, right? Where A is BH and D is H over 2 squared. This thing is just equal to 1/3 BH cubed. It's a good thing that screen is fuzzy because you guys look a little lost. Am I right? All right. Anyways, that's just some statics.
I just want to. I got a question. I just want to clarify this in my head. What we just did was we calculated the yield moment and the cracking moment of a concrete beam, which had rebar in the bottom with some kind of reinforcing steel.
Right.
And what we have is a cross section of the beam, which is the crack section. That's what we're looking at. The bottom.
That's correct.
2/3 is cracked.
That's
The
correct.
top bit is not cracked. Okay.
Okay, so we basically went like exactly what you said. We found out two of its strength limits. Number one was the cracking strength, and number two was its yield strength. Now, the third state is, well, if you continue to load it, obviously you're going to take it out to failure. Okay, and that's its ultimate strength. Okay? So what happens in ultimate strength? Well, the cracking may go up a little further. Your concrete here in compression is now a distance what I call D, or C, is depth of the rebar again is D. Strain diagram looks like this. Under ultimate conditions, the strain in the concrete is 0.003. Always. That's what ACI tells you what to use. Your linear strain diagram goes back such that the strain in the layer of steel exceeds epsilon sub y. So we know that the stress in that steel is equal to Fy. Now, when the concrete goes into compression at ultimate, what we're going to use is the Whitney stress block. And what this has to do is to take 85% of FC prime over a depth A, which is equal to beta 1 times C, I have that on another sheet, times the width B. Okay? So this is our stress diagram. The force, obviously the stress from the concrete, this gives us C sub C, and the tensile stress in the steel gives us T. The moment arm in between these two is JD, so to find the moment capacity, it's just T times JD. Okay, and I'll show you how to calculate that now. Again, start with equilibrium. C is equal to T. Since we know this guy yields, it's just the area of steel times Fy. So if I gave you a section with width B, height H, and an area of steel here at the bottom, all being known, you can find for me C and T. Okay? Just from this expression. Now, C sub C, we also know, is 0.85 FC prime times A times the width B. Okay? So if you set that into this equation, what you can do is you can find this compressive depth A. It's equal to AS Fy divided by 0.85 FC prime times B. Okay? Alright, again, I told you what K was. K is just A divided by D. So if you put that in, K turns out to be equal to AS Fy divided by 0.85 FC prime B times D. Alright? Now, once you know K, again, I told you that the ultimate moment capacity is just T times JD. T is equal to AS Fy, and JD is the moment arm between those two forces. Okay, and if I know this distance is A, C I know has to act at A over 2 from the top, and if the full distance down is D, then it's just D minus A over 2. Okay, or to put that in terms of a quantity of K, this gives me D times 1 minus K over 2. Okay? Again, what it's going to look like moment curvature is you're going to load up to its cracking point along one stiffness, which I'm going to define as EI gross. Once it hits the cracking strength, the concrete cracks, you start to lose stiffness until you get to yielding in the steel. Once the steel yields, you follow another stiffness all the way out to ultimate. This is sometimes called the backbone curve. For design, we're worried about ultimate. For deformation control, we worry about cracking. We want to know where we're at over here because look at the stiffness change. The stiffness results in increased deformations if the stiffness degrades. Okay? So, why did I present all that stuff? I don't really know. I wanted to give you flow charts, and that's what I'm going to give you now. But you have to sort of understand where it all comes from. And I know it's probably been a lot of years when you guys have looked at this, but I still think it's worth it for you because it's going to get you in the right frame of mind for this exam.
Before you do that, can I ask a quick question?
Sure.
Back on that moment curvature graph. The difference between cracking, yielding, and ultimate. If we crack means we've held up until a certain point, and then the inside components of the concrete begins to fail until we go to, and then from there to yielding, it's the concrete is still holding, but it's weakening. Is that what we're saying?
Okay. Just imagine you got a simply supported beam, concentrated load at the middle, looks something like this, right? Alright, say you start P off at 0, and you start to load it up. The bottom of this beam is going to start to go into tension. Well, when's it going to crack? It'll crack when it hits its cracking strength, right? So, it's going to load up to this point. Okay? And then once you exceed that point, the concrete in the lower part of this beam is going to crack. So it's going to start to propagate upwards. Alright, it'll go upwards until this steel down here at the bottom begins to yield. That's our second limit. Okay, and then you keep continuing it on until you get the ultimate strength that occurs in both the concrete and the steel at the bottom. And that takes you out to the very last point. Okay?
Yes, sir, thank you.
Alright, now this is an analysis of a singly reinforced rectangular beam. You're given BD, the area steel, FC prime, and FY. We're going to take the modulus of the steel to be equal to 29,000 KSI, and we're going to assume that the rebar yields. Now, there's specifications in the code that tell you that bottom steel has to yield, and the reason is for ductility. Okay, so by you making the assumption that the bottom steel yields, that's a good assumption. All right. Now, if we assume that it yields, K can be calculated from this formula. It's just ASFY divided by 0.85 FC prime BD. And if you look at your given, it's all known. Okay, so you're finding your compressive depth in the concrete. Then what you need to do is you need to check this versus K minimum. And K minimum is defined in the code as 200 divided by 0.85 FC prime. So if your K exceeds K minimum, then you have enough area steel in your section, and it's not under design. If K was less than K minimum, then you're going to have to increase the amount of steel. Okay? Now, once you know your K, you check it versus K minimum. If it was no good, then the section's inadequate. You need to increase the reinforcement ratio. If K is greater than K minimum, all right, you can continue on. Now, we're going to compute beta 1. Beta 1 is 0.85 minus 0.05 FC prime minus 4,000 divided by 1,000. FC prime has to be between 4,000 and 8,000 PSI. Okay, and again, for normal concrete, it falls into that region. Beta 1 is going to turn out to be between 0.65 and 0.85. All right, if you're using 4 KSI concrete, the beta 1 is going to be equal to 0.85. Now, the next step we're going to do is calculate K balance. All right, K balance is beta 1 times 87,000 over 87,000 plus Fy. Where Fy again is in PSI, it's the steel, and typically it's going to be either 40 or 60,000. Now, is K less than 75% of K balance? All right, now what I told you guys before is the code puts a stipulation to make sure the bottom steel always yields. This is it. Balance failure is when the concrete and compression and the steel at the bottom fail at the same time. By making K 75% less than that value, we ensure that bottom steel always yields. Okay? So if K is less than K balance, 75% of K balance, the mobile capacity is found from this formula. If K is greater, then the section is inadequate and we have to increase the section. Alright, we have to add more concrete or we have to decrease the amount of steel. Okay, so that's how to analyze a beam. For design, what we know is that our nominal capacity times this undercapacity factor, phi, must always be greater than our demand. And the demand is the load factors times, the dead loading plus the live load. Okay, and again, phi for bending is 0.9. K must always be less than 75% of K balance. This ensures a ductile failure. Okay, ultimate strength refers to failure. Select the height of your section based on deflection requirements from Table 9.5A of ACI. Okay, if you use this table, it's going to specify for you, it's going to approximate the depth of your section. Okay, so if you just have you have to design a beam, you know, what depth do you go with? Well, here's the first place to start because it'll give you some idea. Okay, so you go to your Table 9.5A and you can come up with some approximate depth. Choose FC prime, FY, the width of the beam, and the area of steel. Typically the B to H ratio, so in other words the width to the depth, is in an area of 1 to 1.5 to somewhere between 1 to 2. Okay? Again, some more... Yes?
On our beams, we always want the steel to fail first before the concrete then? Is that what you mean by a ductile failure?
Right. Just think about the stress strain for the concrete when it's unconfined. Right? Once it reaches peak strength, it goes right down. And then think about what happens for the steel. It hits its yield point, and then it goes on forever. All right? The steel is more ductile, so we would want the failure to develop there.
Okay.
Okay? Okay.
Got it.
The Lindbergh book also has another good chart, and in this thing it has the bar size versus the number of bars in a single layer of reinforcement. So in other words, if you have a section and you have, say, 5 number 8 bars, okay, you design your section, you need 5 number 8 bars. If you go down this chart, what it's saying is that the width of your beam has to be at least 12.9 inches, okay, and that'll satisfy all the cover requirements and things like that. All right, if you found out in your chart that you needed 5 number 8s and the width of your beam is only 12 inches, well, you can't use 1 layer. You got to go to 2 layers. Either that or increase the width of your beam. Okay, so this is a handy chart. Okay, here's the design process. We first of all determine your demand moment, and again, this is from static. And typically this is going to be 1.4 times the dead load plus 1.7 times the live load. You select FC prime and FY. Case number 3 is you're going to select K. Let's say that K is 30% of K balance.
That's just a good number?
That's a good number because we know that the maximum that we can use is 75%, and we really don't want the concrete to fail, so 30% of K balance is sort of like an optimum value. So let's start there and see if that works. Okay? K balance, again, we find from this formula. Now, assume a B and find D. Alright, you have an equation here. And what this is just the moment capacity, which is equal to C times JD, except it's all carried out for you. BD squared is equal to the moment demand divided by phi divided by 0.85 FC prime K times 1 minus K over 2. We already assumed K up here. We know our design moment. We know FC prime and we know phi. So if we assume a B, we can calculate D. Alright, and again, we want to keep this ratio in between these two limits. Now to find the required area of steel that you need, it's just the moment divided by phi divided by Fy D times 1 minus K over 2. Okay? And again, you know everything on the right side of this equation. The minimum area of steel, again, the code requires a certain amount. It's the 200 times B times D divided by Fy. Alright, so you found your required amount. Is it greater than the minimum? If it's yes, then select it from the tables. The table that you just had previously was a good example, and there's others in the Lindbergh book that are also good examples. Alright, now once you know the area of steel, calculate your K provided. K provided is just rho provided, where rho is the area of steel divided by BD, times Fy divided by 0.85 FC prime. Okay? The moment provided now you find from this equation, alright, the full height that you need in your section. Remember, you assumed a B, you calculated a D. Well, what's the total height of your section? Well, that's the depth to the reinforcement, plus any cover, plus the diameter of a stirrup, plus half the diameter of the longitudinal bar. Okay, so that's how you determine your actual H. If this number turns out to be 18.3, well, you can't go out and build a beam that has a depth of 18.3. You got to make it 19. And when you make that 19, if the cover, the stirrup, and then the bar doesn't change, the only thing that's going to change is D. When D changes, K changes. All right, so you calculate your new K, and then calculate your new moment. Okay? to show you what this will look like. This is the full depth of your section H. Your bars are down here at a distance of D. Stirrup, remember, wraps around these bars. If we say this is a number 3 bar, that has a diameter of 3/8, okay, plus the cover here at the bottom. So, and the half a bar diameter, again, because D only goes to the centroid of these bars, it's half this bar diameter plus the stirrup plus the cover. Okay? The stirrup is for shear. Okay, now I haven't talked about shear yet. This has only been for flexure. That's coming up. Okay. Now, if you know an H, so you got some architect and he says this beam can be no deeper than 2 feet, then you know your H. It's restricted. All right? And what we don't know is the B and the A sub S. So what we're going to do again is compute the demand moment, select your FC prime and FY, assume a B, and calculate the D based on the known H. Okay? Now you can calculate K from this expression. Alright, once K is known, we have to check that, make sure it's less than 75% of K balance. And once that's the case, the area of steel required can be found from the same formula from the previous sheet. The minimum area of steel is 200 times BD divided by FY. Select the area of steel now that you need based on the required amount. And then find your K provided. Again, that's rho times FY divided by 0.85 FC prime. And then you can calculate your moment provided. You make sure this exceeds the demand. These last 10 pages is just manipulating the previous equations from those 3 parts, or the three stages from previous. Okay, that's all I did was change the equations around to fit the design process. I lose you guys?
Hey, Joe?
Yeah.
I'm going to assume that all the numbers, in the Lindenberg book, he goes through all the different cover requirements, bar spacing and all that. I'm going to assume that again, is basically to code.
It is.
He gives you all the...
He puts in all those numbers for you. That's correct. Alright, now here's a quick example problem. It says design a rectangular beam with tension reinforcement to carry service moments of 34,300 foot-pounds of dead load, 30,000 pounds of live load, foot-pounds of live load. FC prime is 3,500 PSI. FY is 40,000 PSI, and number 3 bars are used for shear. So you have number 3 stirrup. Okay. The dead load we know is this. Yes.
Joe?
Yes.
Now, is this starting to look like a problem now? I mean, that's something that we might see.
This looks like a problem, except again for line 2 here, where they're giving you the dead load moment, the live load moment. Typically, they won't do that. You'll have to find those numbers from statics.
From a shear and bending moment.
From a shear and bending moment diagram, right? You compute that from statics, and then you can continue on with the rest of the problem. So this is, yes, this is a problem that could be on the exam, something like this. Okay, so you can compute your demand. It's the 1.4 dead plus 1.7 live. If you multiply everything out, you get 99 kip feet. Okay? Again, select K. Using my flow chart. K is 30% of K balance. If you plug in your numbers, you substitute it in FY here, it turns out to be 0.206. Alright? Now, based on this K and your demand moment, and the FC prime that you assume, or you calculated, BD squared turns out to be about 2,400 inches cubed. So if I assume a B of 9 inches, D turns out to be about 16.35. And again, that's in the right range, right? Between 1 to 1.5 and 1 to 2. Now, based on this BD, let's calculate the area of steel required. It's the moment divided by phi, divided by FY, D times 1 minus K over 2. This, when you multiply everything out, you watch your units when you plug them into these equations, the area of steel turns out to be 2.25 inches squared. Okay? The area of steel minimum is 200 BD divided by FY. If you substitute those, you get 0.74 inches squared. You see that what's required exceeds the minimum amount, therefore we have to design for the required. Okay. Now, 3 number 8 bars will provide 2.37 inches square of area of steel. So that'll work fine. Now, let's calculate the full height of our section. It's the depth D, which we already found from before, right? That's 16.35, plus half the diameter of a number 8 bar, which is a ½ an inch, plus the diameter of a number 3 stirrup, plus the cover. The cover is 1.5 inches on a beam. So when you add all these things up, you get 18.725 inches. Again, you can't design a beam to have this depth because a construction worker will think you're nuts. Okay? What you got to do is make it 19. So if you make this 19, the D actual changes again. So it's 19 minus the cover, minus the stirrup, minus half the bar diameter of a number 8. This gives you 16.625. K provided now is the area of steel divided by BD, Fy divided by 0.85 FC prime. This turns out to be 0.213, which again is less than 75% of K balance, so it's doing good. The actual moment now is ASFY D times 1 minus K provided divided by 2. And if you multiply this by your under capacity factor for bending, which is 0.9, what you get is 105.6 kip feet. This is the most that you can have for demand. Our demand was 99, so our capacity exceeds the demand. The beam is satisfactory for bending. Okay? That's sort of a quick example problem for bending. Alright, now, the next piece goes into T-beams. And this is more or less along the same lines of the previous. Now, the first point I want to talk about is the effective flange width. If you're building a floor where you have beams and slabs that are poured together or monolithically, it's reasonable to assume that part of this slab is going to act with this beam as it bends. Alright? The code tells you what value you can use here for B sub T. And what it says is that B sub T has to be less or equal to L divided by 4, where L is the length of the span of the beam. It also has to be less than B, which is the width of the beam, plus 16 times the thickness of the slab. And it must also be less or equal to S0, where S0 is the distance between the two beams to its next adjacent beam. Okay, and I put that here on the drawing. If you have an isolated T-beam, now isolated T-beams are used a lot in bridge construction where beams are prefab and the T is actually a T shape. It's like an I shape. Alright? And there's certain specifications for these types of structures. Now, B sub T must be less than 4 times the width of the beam at the bottom, and this width at the bottom must be less or equal to 2 times the thickness of the slab. Okay? If you're on an exterior beam, then you have what's called an L beam. Alright? And the code says that B sub L must be less than B plus L divided by 12, must be less than B plus 6T, and it must be less than B plus S0 divided by 2. Okay? So this is how we're going to identify our section.
So what you're really saying is, you don't care how long it really is, but you just don't get to count, but that much.
That's correct. All this slab over here you can't use in your bending moment calculations. Why is this going to be good? Well, that's what I'm going to go across to my next sheet. Remember, when concrete goes into compression, that's a good thing. So look what happens in this T-beam, how the compression zone spreads out into the slab. Well, we can take advantage of that, because the more compression you can put up here in the flange, the bigger your moment arm, JD, is going to be. So your flexural capacity would be increased. Alright, so that's the big thing with T-beams.
But no fair taking more of it than you really deserve.
Right.
That's why you limit the top B.
That's right.
Okay.
That's right. Because not all the time, the slab, when you get 50 feet away from the beam, obviously that slab doesn't act with the beam. Okay, B is found to, that width is found to, for the flexural capacity of this beam, that the slab could be included up to this width B and nothing else. Alright, now...
I have a question.
Yes, sir.
The difference between a monolithic and isolated beam, once again, is that the monolithic beams are all joined, and the isolated beams are physically separated. That's
correct. The slab... Alright, so for example, monolithic would be, you go out, you have your formwork, and in this formwork you're going to have room for beams and slabs to be poured together. Okay, so the beam and slab are all going to be poured in the same pour. An isolated T-beam for example, would be something that's prefabricated and brought out to the site. It's like an I shape, except it looks like a T. Okay, and then the slab would sit on top of that. That's used a lot in bridge construction. All right, now, the way we're going to find this moment capacity, and I'm just going to summarize this real quickly, is we're going to do it in two parts. All right, we're going to find out what the moment capacity of this section is. So in other words, let's neglect the compression in the web. Let's just consider the part in the flange. And then what we're going to do is we're going to add this moment capacity to the moment capacity when the concrete in the web goes into compression. So we're going to sum these two parts. Okay, now, the first note is that K times D. Remember, K is the depth to the neutral axis. KD is the depth to the neutral axis. This only applies when KD is greater than the thickness of the slab. When it's less than the thickness of the slab, that's all it is a singly reinforced beam. Okay? Of width B. Remember what we did for a rectangular beam. We had a certain part of it, the top part of it was in compression, right? And then what we did was we figured its width and its depth, and then found the moment arm between the area steel and the centroid of the compression zone. Well, what happens now if only the flange is in compression? Well, you still have a rectangular block that's in compression. So it would be 0.85 FC prime times B times the depth that's in compression, as long as it's only in the flange. If it dips into the web, then you use this procedure. Okay? So what we're going to do is we're going to add this case to this case. Alright, well, what's the moment capacity of this first section? Well, what's the force C sub C? It's 0.85 FC prime, that's the stress, over the area in which it acts. Well, what's the area of these two rectangles? The width is B minus little b divided by 2 on this side. On the right side, it's the same. Okay? So it's the 0.85 FC prime, B minus B, when you add these two parts together, times the thickness of the slab, T. Okay? And where does that compression force act? It acts at the center of the slab, right? At its centroid. And the moment arm now is just D minus T over 2. Okay? So that's the force C sub C. D minus T over 2 is just the moment arm. Then we have the part here from the web. And again, this is the same thing as a singly reinforced beam. 0.85 FC prime B times KD, that's the force, times the moment arm, which is D minus KD over 2. Okay? When you sum these two parts together, that's the total moment capacity. Now, you notice here, I had 3 bars in the original section. In this section, I only drawn 2, and in this section, I drawn 1. Equilibrium says that C must equal T, right? Here it is. C sub F, that's the force in compression, has to equal T, where T is equal to AS times Fy. So if I divide the force in the flange, which I know is 0.85 FC prime, big B minus little b times T, divide by Fy, I can find the area steel required for our first shape. And then what I do is do the same thing for the second shape. I find the force in the compression here, divide that by Fy, and that gives me the area steel required for the second shape. If I add those two area steels together, I get my total. Okay, so that would be the total required. Now again, this only applies when KD is greater than T, and when it's less, we're just going to use a singly reinforced beam.
So one quick clarification. Your C sub F is your Mn minus your last part of the equation, D minus T divided by 2. That's your C sub F.
C sub F is the force.
0.85.
Right, is 0.85 FC prime, big B minus little b, times T. Okay, it's the stress in concrete. It's the force that the concrete's in compression. The stress we know is 0.85 FC prime, and it's uniform over this area. The area is just big B minus little b times its thickness T at the slab. Okay, so this thickness here is T. See that now?
Another question.
Okay.
Yes, sir.
How do we know what part of the slab concrete is acting in compression? I mean, here it's already shaded for us, but
That's correct.
How do we know this on the exam?
Okay, all right, now, first of all, you'll make some assumptions. I'll show you a design chart later on how to do this. You'll make some calculation, all right, and the first thing you're going to do is, well, you'll assume that only the flange is in compression. Okay, if you make some assumption on that, and it's true, then you can design it real quick. If it's not, you're going to have to calculate this KD, and I'll show you how to do that next. Okay?
Yep.
Anybody else? Okay, now, oh God. Okay, T-section design. All right, now, the moment capacity in the flange, I already told you was the force and compression in the flange divided by, or times its moment arm. That's this, okay? Now, if you know your demand moment, and you made some calculation that KD is greater than T, okay, you find your moment capacity in the flange. The moment required in the web is just a demand divided by phi minus what was found in the flange. Okay? Now, next thing you do is you compute your compression block, that's K, from this formula, and that's based on K in the web. Design the area steel required for the flange, that's the moment divided by its arm divided by Fy, or C sub F divided by Fy, which is equal to this. The area steel required in the web was the moment in the web divided by its arm divided by Fy, and then to find the total reinforcement, you just sum the two together. Alright, and again, you have to check this versus the minimum, and then the next step is you have to make sure that rho is less than 75% of rho balance, or K is less than 75% of K balance. It's the same thing. Okay, it's just manipulating equations. Now, K balance I know is beta 1 times 87,000 over 87,000 plus Fy. The compression force at balance is the part from the web, actually it's the part from the flange, correct that on your notes, plus the part from the web. The part from the flange we can find from here. The part from the web is found from here. Okay? That's with this value of K, substituting into here. So the area of balance, again, C is equal to A times Fy, so you can find that area of steel. It's just C balance divided by Fy. Now what you need to do is check your area of steel total that you just found versus 75% of this area of steel at balance. If area of steel is less than that, then you're okay for design. Okay? Now, I had a good example problem, but then I took it out. Typically what you would first start off and you would say, just like you would in a regular singly reinforced beam, is you assume that the bottom steel yields. And if you do that, you can calculate D. Alright, you can calculate your KD. And then you would check to see if it's only in the flange or it dips into the web. If it's only in the flange, you just consider the singly reinforced beam analysis. If it continues into the web, then you use this previous sheet that I just showed you. Okay? Doubly reinforced beams is the same way. What we're going to do is do it in two parts. Again, the section looks like this. We have a compression force in the concrete, a compression force in the steel, and what we're going to do is handle it in two parts. Number one is we're going to forget the compression steel at the top and compute a moment capacity, and then what we're going to do is we're going to consider the compression steel and find another moment capacity and then add them together. Okay, for design, what we're going to do, again, flowchart type procedure, you're given a demand moment, a B, a D, an FC prime, and an Fy. Okay? Determine the maximum moment that can be taken by a singly reinforced beam. Alright, so that's step one, and the way we're going to do this is like that other flowchart. Again, compute your desired K. What I'm saying is let's use K max, which is 75% of K balance. Let's find the moment capacity, what I call M1. Okay, and that's based on this K max from up here. 0.85 FC prime BD squared K max times 1 minus K max over 2. The area steel required for that, you find from this formula. And now, determine if doubly reinforced section is required. Up to here was just singly reinforced. If this thing provides you enough moment, then you're done. Alright, if it doesn't, then you need to design compression steel at the top. And the amount that you need is the demand divided by phi minus what we just found from up here. So the total area steel on the negative side is found from this equation. All right, and the total area of steel now required on the positive part is the part that we found from the first case, plus the part that we just needed now for the second case over here, summed together. Okay, and I know this isn't enough explanation, but hopefully the flow chart will help you during the exam. All right, it takes me a whole semester to do this. All right.
Hey, Joe?
Yeah.
We feel a little better.
I don't understand under what circumstances you'd want to go to doubly reinforced versus just increasing your other dimensions or increasing steel in the singly reinforced case. I mean, why? It seems to kind of defy logic by putting your steel at the top end of the member.
Okay, you're right. I mean, for flexural strength, the amount of compression steel that you put at the top really isn't that effective. Okay, if you think about it realistically. But there's other problems that when you add compression steel, for example, when you put compression steel at the top, your sustained loads, so in other words, long-term type loadings, concrete creeps when it's under loads for a long period of time. Now, if you put compression steel at the top, that steel is going to help resist some of those compression forces, and steel does not have very much creep. Okay, so the steel is going to help the beam with creep characteristics. So that's really the main reason. Another reason is you have to normally add stirrups in a beam for shear reinforcement. And if you just put steel at the bottom, well, what's going to hold those stirrups up? Pretty much nothing. So typically they run bars across the top just to hold the cage together, if for no other reason alone.
So you might as well get the profit out of the bars.
And then you can get profit out of the bar. Typically for design, if I was you, I'd do exactly as you'd say. Forget negative steel, because we know it's conservative. If we just assume that you have positive steel, all right, we know that we're providing at least a certain amount, and if we make sure that that amount's greater than our demand, then it's okay. If you have compression steel, well, your capacity is just going to go up even more. Okay, but if they ask you a specific example, on how to design a doubly reinforced beam, then you're stuck. You really have to do it this way.
Yeah.
Okay, the ACI code also presents demands if you don't have access to a computer program, and this may be especially beneficial during the exam. All right, if you have a structure that looks like this is in section 8.3.3 of the code, and this is some of the terminology. This is an exterior face of exterior support. Here's your beam running across the top. This is an exterior span. This is an interior span. You have a discontinuous end. This is a continuous end. You have an interior face of exterior support. You have an exterior face of first interior support. That's over here. And there's a bunch of conditions that you have to meet. Number one is that the spans are a certain length. You have at least 3 of them. That the dead loading is not considerably greater than the live loading or something like that. You can check in 8.3.3 about those. But if you meet those conditions, what you can use are these formulas. And what it's saying is if you have a beam, say for example you have columns here and you have a beam running across the top of the columns. Well, the design moment of this beam at this point is 1/16 W sub U times L sub N squared, where WU is the factored uniform loading and L sub N is the length of the span. Now you guys don't have this on your sheet, so you may want to write that down. The moment is equal to C sub M times WU L sub N squared, and the ultimate shear demand is C sub V times WU L sub N divided by 2. C sub M and C sub V are found in these figures, okay, depending upon what you have. And you can look at the captions to try and figure out what type of structure you have. Now these are all for continuous beams.
So could you zoom in on that formula up there?
Okay.
You can't really see it on the screen.
Okay.
Couldn't
read that, huh?
Beautiful though. I told you you had to use at least 2-point font.
Okay. I'm going to take 5 more minutes and then we'll have a break, all right? Development length. We're gonna do this quick now. You thought that was quick. Wait till you see now. Development length. If you have a number 11 bar or smaller, in section 12.2.2, again, this is in the Lindbergh book, the development length of the bar is this formula, or 12 inches, whichever's smaller. Then you have factors. So in other words, if you have spacing, and for spacing of the bars and cover, there's certain stipulations that you must have. If those are all satisfactory, then the factor is 1. If the cover is less than a certain amount and the clear spacing between the bars is less than a certain amount, then the factor becomes 2. So the amount of development that you'll need is what you calculate here times these factors.
Or at least 12 inches?
Or at least 12 inches.
Okay.
Now, if neither of these two categories are satisfied, the factor becomes 1.4. If your clear spacing exceeds 5 times the diameter of the bar and the cover is greater than 2.5 times the diameter of the bar, the factor is 0.8. Okay? If you have top bars with 12 inches of cover below them, the factor is 1.3. If you have excess reinforcement, so you design a section so that the moment capacity is significantly greater than demand, well, you can take that into account into this formula. So you can have a reducing factor here. Epoxy-coated bars has a factor. Lightweight concrete has an additional factor. Okay? That's a tension development length. What happens when they're in compression? Well, there's different formulas and different factors. That's in section 12.3. What helps development length? Development length is like how a concrete... Hit it to me.
Gotcha.
Development length is if you have a bar buried in concrete, well, how much of this bar do you have to bury in the concrete before yield strength occurs? Can I just stick the bar in an inch and expect to develop yield strength in the bar? Probably not. You have to put it into the concrete a certain amount. Okay? So what happens if you don't have enough length in the concrete? What happens if... how can you change that development length? Well, one thing you can do is put a hook on the end of the bar. And when you put a hook on there, what it's going to do is it's going to provide more resistance to pulling out. Okay, and you'll see that in these factors. So there's a basic development length that you need on a hook. That's the 1200 dB divided by root of FC prime. You also have a bunch of factors for this thing. And what it must be is that the final development length when you use a hook has to be either greater than 8 times the diameter of the bar, and also greater than 6 inches. Here are all your factors. You guys can read that at your leisure, which I know isn't much. As far as cutoffs go, well, how far do you continue bars? If you design the negative moment at a point, do you continue those negative bars to infinity? Well, you have to follow the moment diagram. Okay? All bars must cover a design envelope, or the moment diagram, and provide an additional 12 times dB plus D, whichever is larger, plus sufficient development length. So in other words, if you have a continuous beam, and the moment diagram, I didn't do that right. Let's start again. The moment diagram looks something like that. Okay? Well, you designed the steel for this point, and say that turns out to be 3 number 8 bars. Well, we already know that you have to provide at least a certain amount of development length on each side before the bar becomes fully active. Plus what the code is saying, you have to provide an additional distance of either 12 dB or D. You guys can't see that at all, can you? No.
Joe, Lee taught us last week or yesterday that you got your curves drawn wrong there. You're going down that steep ski hill, so
you
need to draw that curve the other way.
Did he tell you about this?
Yeah.
Why do I put it like that? I'll give you a quick answer. Where do you need to put the steel in this beam?
On the upside down side that you drew it upside down.
Don't confuse everybody.
That's right, I agree.
Here's your moment diagram. Here's your moment diagram. It's plotted on the tension side. So wherever you see your moment diagram, on this part you see the moment diagrams on the bottom. So it's telling you the bottom of the beam is in tension. So you need to put steel on the bottom. Over here, put steel on the top. Bottom, top, etc.
And you might mention that one of the guys told me that one of the questions was, where's the steel go?
That's true. You know, they could give you a continuous beam and say, where would you need to provide flexural reinforcement? The biggest thing you think about, remember, concrete's terrible in tension, so put steel where it goes into tension. Okay? There's also 2 sheets on tension splices, lap splices. Okay? It's more or less the same thing, and it depends on the area of steels that you have in your section. You can go back and take a look at those. What it's telling you is that it's based on a development length. All right, you're either using the development length itself, or 1.3 times the development length, or 1.7 times the development length. Okay, lap splices is because if you have to have a bar, say for 60 feet, well, maybe you can't find a bar that's 60 feet long. You can only find it at 20 feet. So what you have to do is you have to overlap them a certain distance. That's what we're finding here. Okay? And how about shear reinforcement? Shear reinforcement, you have your nominal capacity. It's the capacity from the concrete. Remember from the first couple of sheets I told you that the shear resistance in concrete was 2 root FC prime. And then if you put in stirrups, there's an additional resistance. That's V sub S. Okay, again, for beams, the resistance in the concrete is 2 root FC prime B times D. If you're in a column that's in compression, the equation changes slightly. You get this additional term here, which is N divided by 2,000 times AG, where AG is the gross section area of the concrete, and N is the axial compression load. Okay? Everything else here you know. The V sub S is the area of the stirrup. So if you're using a number 3 stirrup, basically you're going to have 2 times the area of the bar. Okay? Because for that beam to fail in shear, okay, if you got yourself a simply supported beam again, cracks are going to develop this way, okay, in shear. And if I look at one section, there's my stirrup, this crack is going to go through both of these bars. So that's why you got 2. Alright, so if you're using a number 2 or number 3 bar, you're going to be using 2 times 0.11 into this formula. Okay? Now, for design, what we're going to make sure again is that the demand is less than its nominal capacity times this factor for shear, which is 0.85. Now, if the demand is less than phi times the part from the concrete divided by 2, then there's no shear rebars required. Okay, the concrete can take it all. If the demand turns out to be greater than 1/2 of its resistance in a concrete, but less than the total resistance in a concrete, then you must provide a minimum amount required by the code, which is this formula here. The area steel minimum is 50 times B times S divided by Fy. Okay? The spacing of these bars must also be less than either dB over 2, and it must also be less than 24. Okay? If the demand turns out to be greater than the part from the concrete, but less than the part from the concrete plus this minimum provided from the previous part, then again it's just the same. Alright? Your area steel required is just the same as before. If you now jump to the next region where you exceed this part, but it's less than the part from the concrete plus 4 root FC prime BD, then the steel required is the demand minus the part from the concrete, and the area steel required you can find from this formula. Now, again, if you're using a number 3 bar, the AS required you can say is 2 times 0.11. You know the shear required, you know Fy, and you know D. The only thing you're going to calculate now is the spacing of the bars. And this spacing must be less than D over 2 and must be less than 24. If your range falls greater than 4 root FC prime but less than 8, then you can use this procedure. Now the thing that changes here is the maximum spacing. We went from D over 2 and 24 to D over 4 and 12. Alright, this is where shear is really dominant in the behavior of the structure. Shear is a very brittle failure mechanism, and we try and avoid that as best as possible. And as far as a critical distance goes, what we're going to do, if you have a beam that's continuous over a column, all right, your shear diagram may be something looking like this dotted line. Okay, the critical distance for a shear is a distance of D from the column face. So here's your column face. You move a distance of D over. You design for this amount right here. You don't have to design for the peak. You can design for this amount. The reason is because of the way this thing is going to fail. All right, remember, shear cracks occur at a 45-degree angle. So look at the length of this line as compared to the length of that line. You have more resistance out of this line, even though the demand is greater. Okay, so the critical one's going to be right here. And there's also some anchorage requirements for stirrups, and that's just procedures from the code. You can catch up on that. And I also showed you, I told you about a table in the code, which is 9.5A for deflection control. If you have a one-way slab, the minimum thickness that you need for the slab for a simply supported beam, one-end continuous beam, both-end continuous, and a cantilever, depending upon what you have, you find from these equations. If it's a one-way slab, it's the top one. If it's a beam or a rib slab, you use the bottom one. Okay?
A rib slab being those little pan-looking things?
Yeah, a rib slab is a whole bunch of beams running underneath the slab that sort of act together monolithically. Okay? The design for one-way slabs is just like designing a beam. Okay? Except what we're going to do is we're going to assume that we have a width in the beam of 12 inches. And what we're going to do is find the required area of steel that's needed in that small little piece. Alright? It's the same flow chart that I showed you for beams, except it's only going to be 12 inches wide. Okay, the yields will be in inches squared per foot, so you may put down 2 number 8 bars per foot of slab. So you'll space number 8 bar up at 6 inches all the way across. The maximum bar spacing for bending is either 3 times the thickness of the slab or 18 inches. You also have to check for crack control. I'll do an example of that. There's shrinkage problems in concrete that you also have to account for. If it bends in one direction, then it's also going to shrink in a direction 90 degrees from the bending direction. So you have to provide steel in both directions. And the area of steel, another quick table, can look something like this. Again, this comes from the Lindbergh book, and this is useful when you design slabs. Okay, let's take a couple-minute break. Sorry about keeping it a little too long. I think we'll finish on time. All right, so how about between 3 and 5 minutes? I got...
Are you halfway through?
Alright. You're not going to be chopping on M&M's now as I'm trying to teach, are you?
Well, I'm not gonna do it on camera.
Okay.
Because Chris is going to ask me if I brought some for everybody.
Okay. Alright, we're going to continue on. This is still with beams now. And the one that I stopped on was for crack widths. All right, remember I told you when the loads exceed its cracking strength, there's going to be cracks that develop. And if you have a beam that's cracked, does it necessarily mean that it failed? No, right? Because it can go up to yield and then it can go all the way out to ultimate. So it hasn't necessarily failed yet. But when you're dealing with bridges, etc., that are outside to the corrosive environment, what you can get is deterioration in the concrete. So what the code tries to do is limit this crack width. And here's your formula. It's Z is F sub S, the cubic root of D sub C times A, where F sub S is the service load stress on the rebar. And typically what we're going to use here is 0.6 times Fy. D sub C is the distance from the extreme tension fiber of the concrete to the center of the tension rebar. Okay? So if I draw that down here, here's your rebar. That's D sub C. The A is the effective area of concrete surrounding the tension rebar divided by the number of tension bars. What this is 2 times D sub C, because what it's saying is that while you have tension concrete below and above. Okay, here's also D sub C. So it's 2 times D sub C times B. That's this area. All right, and then we divide this by the total number of bars across this layer. Once you plug these in, if your Z turns out to be greater than 175 for an interior exposure and 145 for an exterior exposure, then the beam should be redesigned. Okay, if you're less than that, then you're okay. This could be a legit problem on the exam. I believe when I took it, I had like a simply supported beam or a cantilever beam, and I had to find the demands. I had to design it for flexural strength, shear strength. I had to check for cracks and check for deflections. Deflections is the next part. All right. If you use table 9.5a to find its thickness, you do not need to calculate deflections. If you don't, you have to use an equivalent moment of inertia, and this is for deflection control. It says I equivalent is M crack, this is the cracking moment, divided by M max, which I'll talk about in a second, cubed times I gross, plus 1 minus the cracking moment divided by M max cubed times I crack. Alright, now, the cracking moment we found from before was 7.5 root FC prime times I divided by Y sub B. Okay, go back into the first stage and you'll see this equation. M max is the maximum unfactored service moment. Remember, we're trying to find deflection, so is it really necessary to compute deflection at the ultimate? What we're worried about is when a person walks on the floor. We just want to make sure that this beam doesn't bounce all over the place. So this is based on service loads. You do not have to multiply it by any load factors. I gross is the gross moment of inertia, and typically it's just a rectangle. It's just BH cubed over 12. Y sub B is the distance from the neutral axis to the extreme tension fiber, and in this case it's normally half of the height of the beam. And I sub crack is the crack moment of inertia. Remember, we discussed that also. That was that when we had that 1/3 base times height cubed thing. All right, that was that formula right there. All right, so you can compute your I equivalent, and once you got I equivalent, if I say you got a simply supported beam, everybody's going to bring in with them an LRFD manual. And in that manual, it's got deflections for a simply supported beam when you have a uniform load across the top. And if you look into that book, you'll notice that it's going to be a function of EI. You're going to be dividing by EI. The I that you use is this I, the I equivalent. Okay? So you're using the elastic formulas with this equivalent moment of inertia to calculate your deflections. Now, those are short-term deflections. When you got long-term deflections, what you do is you multiply the instantaneous deflections, or what you get from the first part, times this factor alpha, where alpha is this time factor divided by 1 minus 50 AS prime divided by BD. Okay, and someone asked a question before about why do you need compression steel? Well, long-term deflections will be a lot less when you have AS prime. When this term is 0, the factor for alpha is larger. Okay, notice how you divide here. So this time factor, if you're dealing with 5 years or more, the factor is 2, and you'd have 2 divided by this thing over here. All right, now let's do an example. This is a very legitimate problem for the exam. All right, and this is probably something very similar to what I had on my exam. Okay. You have a beam, it's supporting a roof, and it needs to span 27 feet. It's simply supported. It carries a dead load of 1 kip per foot, and that includes the beam weight, and a live load of 2 kips per foot. Assume FC prime and Fy are 60. The modulus in the steel is 3600 KSI. Use the ACI code with maximum steel percentages permitted. Okay, use number 11 bars and design a rectangular beam with a width of 14 inches. Clear cover on the steel must be at least 1.5 inches. They don't have to give you that, by the way. All right, because all that's in the code. And it said not to design for shear. All right, and then part B is, will the estimated crack sizes be within the requirements of the code if the member has interior exposure? So in other words, we're comparing Z to 145. Part C is to calculate the instantaneous and long-term deflections. Now, what we're supposed to do now is to assume that 30% of the live load is to be used when we consider sustained loads. Okay? Now, you have a simply supported beam. What's the design bending moment? WL squared over what?
Gee, I don't know, it's in the book.
8. Okay, if you go into your LRFD code, you can see that. Alright, if you don't know it offhand, just run right to the code. So that's what you're going to see here. You'll see WL squared divided by 8. Okay, well the W is the factor W. It's the 1.4 times the dead load part plus 1.7 times the live load part. This gives us 437.4 kip feet. This is the demand moment. K maximum is 75% of K balance. We know what the formula for K balance is. That's 0.377. Now, again, this is following my first flow chart. BD squared is equal to the moment demand divided by phi divided by this factor. You know everything. Plug them in. Watch your units. You get about 5,600 cubic feet or cubic inches. Now, it says in a problem to use B of 14. When you use that, D turns out to be 20. Okay? The area of steel required, again, from the flow chart, it's the moment divided by phi divided by Fy D times 1 minus K over 2. This turns out to be 6 inches squared. This is the maximum that you can use because you set K to be 75% of K balance. If you try 4 number 11 bars, which the book says to use number 11 bars, the area provided is 6.24. Okay? But notice the maximum allowed was only 6, and we're providing 6.24. Okay? So what we got to do is we have to make more concrete. We have to have a bigger section. So instead of having a depth of 20, let's make the depth 21. Okay, give it another inch. And when we do that and calculate K from this formula, you see that K, which is 0.375, is less than 0.377. So it's okay. Now the H that we need is, again, D plus the cover plus the stirrup plus half the longitudinal bar diameter. Turns out to be 23.7. If we use a 24-inch deep section and recompute D, it turns out to be 21.3. Okay, which again is bigger than what we assumed over here, so we should be okay. Now let's check for crack control. The stress in that bottom layer of steel, I told you to use 60% of Fy. That's 36 KSI. D sub C is the distance from the extreme tension fiber to the centroid of the area of steel. That's 24, right? That's the total height H minus D, which is 21.3. This gives us 2.7 inches. The area then, in your formula for Z, is equal to 2 times D sub C times B divided by the number of bars. Well, what we have is 4 bars. So this A turns out to be 18.9 inches squared. When you plug it into your formula, Z turns out to be 133.5, which is less than 175, therefore it's okay. Okay? Does everybody buy that?
How about that?
Dr. Lowry buys it. Now, the next part is deflection. We know yes. Alright. We need to go into our formula, and basically what we're trying to do is we have to find this I equivalent. And we have to find all these variables in here. So where I'm going to first start is with I gross. And I gross for this beam is just 1/12 the base times the height cubed. The base is 14. I told you the height now was 24. This turns out to be about 16,000 inches to the fourth. The maximum moment is WL squared over 8. Again, but this is unfactored now. For deflections, we're talking unfactored loads. It's dead plus live, L squared divided by 8. It's 273.4 kip feet. This is unfactored. The rupture modulus is 7.5 root FC prime. This gives us 474 PSI. Y sub B is H over 2, or 12 inches. The cracking moment we know is FR I gross divided by Y sub B. Plug these 3 into here, you get 53.1 kip feet. You divide your cracking moment by the maximum moment here, and there's this factor, 0.0073. Okay, when you cube it, that's the number you get. N is the modular ratio. It's the ratio between the modulus and the steel and the concrete. The steel is 29,000 KSI. For the concrete, it's 57,000 root FC prime, and this gives it to you in PSI. This thing here is in PSI. Your N turns out to be about 8. Rho is equal to the area of steel divided by BD. It's 0.209. Okay, remember your formula for K cracking. It was a function of rho and N. When you plug it in, K turns out to be 0.4357. All right, now that you know your cracking moment, you find X crack, which is equal to K crack, which we just found, times D. Okay, that number turns out to be 9.28. Then the crack moment of inertia, this is the 1/3 X times B times X crack cubed plus NAS times its moment arm, D minus X crack squared. This gives us about 11,000 inches to the 4. Okay, so you just found I crack. If you look into your formula for the equivalent moment of inertia, you know everything in this expression. It turns out to be about 11,000. Okay, so let's take a look here. When the section was fully cracked, we got a moment of inertia of 10,978. When it was uncracked, or the gross section, you see it's 16,000 on the previous sheet, right? So you notice the equivalent I that you're using is closer to the crack. All right, and the reason is because the demand moment is very close to cracking. Now, your instantaneous deflection, this is where the LRFD comes in. You pick out that formula, it's 5 times W L to the 4th divided by 384 EI. Okay, where W is the dead plus the live. The length is 27 feet. All of these factors in here are just unit factors, either to get them into kips or to get them into inches. And then you divide by your 384 times EI. When you get is 0.9 inches. All right, this is with 100% of the live load, and that's what the problem told you to do. Now, for long-term deflections, only considering 30% of the live load, what we're going to do is we're going to multiply our alpha times some instantaneous deflection. Well, what's the instantaneous deflection when the live load's only 30%? Well, that's the dead load part plus the live load part, which was 30% of 2. Okay? And then if we divide this number now by the part that we used in this calculation, which was 3, this will tell us the instantaneous deflection when you have dead and 30% of the live load. That number turns out to be 53%. So the instantaneous deflection, all right, is the 53% times the 0.903, which is 0.479. And then when we multiply this by alpha, this gives us our long-term deflections. Now, when in this beam we have rho prime equal to 0, and if it's greater than 5 years, alpha has to be set equal to 2, okay, because the time factor is 2. So the long-term deflections are 2 times this 0.478 plus the initial deflections that occurred instantaneously that we found previously. So what we get is 1.86 inches, and that's with 30% of the live load. So you come on dead and live load, you get about 0.9 inches, and then 5 years later, that displacement could be closer to 2 inches, or that same load. All right, and that's because of creep effects. Now, if you want to improve this number here long term, what you can do is add in rho prime. Okay, and what that'll do is that'll reduce this factor from 2 down to something closer to 1. All right, so this number maybe you can reduce to 1.4 or 1.3. All right. That covers beams in a real fast way. You guys ready to shoot me yet? You thought Dr. Lowry was fast, huh? And I think today's your day off. All right. You know, when you guys go back and take a look at the example problems and go back to my flow charts, you'll see how everything comes together. Now, I know we're just doing this very, very quickly now, but hopefully if you go back and take another look, it'll make a lot more sense. Okay, the next thing is columns. And for columns, there's 2 types, okay? We defined this before. There's tied columns and there's spiral columns. Okay, tied columns are typically for either square or rectangular, and spirals are used for circular shaped columns. Alright, now column members can contain both axial load and bending moments. A beam only takes bending moments. Okay? So a column is different than a beam. It's a different design procedure. This exam, I don't know what type of question that they can ask you on a column. Alright, because it's a very tough calculation. Typically what people do are they use spreadsheets. And I know you can't bring a spreadsheet into this exam. So if they say, well, here's a column that just has axial load on it, then it's a quick and easy calculation. Alright, what you have to make sure is that your capacity, which is phi times its nominal capacity, P sub n, is greater than the demand. The demand we find is 1.4 times the dead load plus 1.7 times the live load. Well, what's its capacity? Well, if the compressive strength in the concrete is 0.85 FC prime, and I multiply by the area of the concrete, which is Ag minus A sub S, where A sub S is the area of steel, okay, and then I add on AS times Fy, this is the maximum compressive force that the column can take. So what you can do is design your column so that it could take the demand axial load. Alright, now again, the demand comes from 1.4 dead or 1.7 live, or maybe if you have some type of wind load. Some notes is that the width or the diameter of the column has to exceed 8 to 10 inches, somewhere in there. It doesn't explicitly say in the code, but I think it's 10 inches is sort of the minimum for building requirements anyways. A sub G is the gross area of the column. Alright, so if it's rectangular, it's B times H. If it's circular, it's pi d squared over 4. As far as minimum reinforcement goes, again, just like in beams, there's a certain amount that you must apply. It's in 10.9.1, again, of the code. This reinforcement ratio, AS divided by AG, must be greater than 1%. You must provide at least 4 bars, and those bars have to be in the corners of the column. Now, there's a maximum reinforcement ratio, and that number is 8%. And if you ever built a column with 8% reinforcement ratio, it's primarily steel. There's no way you're going to get concrete in there. So typically what I say is to try and keep the reinforcement ratio at about 3% maximum to avoid congestion. Now, if you're in a high seismic zone, this may, this number here may go up slightly. Okay, but pouring the concrete's a real pain. The distance between longitudinal bars in a column must exceed 1.5 times dB, and it must also be greater than 1 inch.
Is that center to center, or is that clear space?
That's clear spacing. Okay, so clear spacing between bars. The cover in a column has to be greater than 1.5 inches for an interior exposure and greater than 2 inches for exterior. The strength reduction factors we also talked about, whether it was tied or spiral. And you see here, for the spirals, it's a little better. It's 0.75 as compared to 0.7. And the reason is because you get better confinement out of a spiral, and we also talked about that before. Now, if you have a column that has both axial load and bending, like I told you, there's one way of doing it is to bring in a spreadsheet, and then you can do it. The other way are these design charts. Now, I copied this out of a book, and there was, like maybe 6 or 7 of them, I guess. And I'll try and show you how to use these. Actually, start with the second page. Okay?
Which one?
All right. What I'm going to use, that's okay, yeah. I'm going to use the second page, that top figure. Okay, so this has an interaction diagram when FC prime is 3 KSI. The yield strength in the steel is 60 KSI, and this gamma is 0.6. Now, if you look on the figure, gamma is the centroid to centroid distance between the bars times H. Gamma times H, and gamma for this case is equal to 0.6. Alright? Now,
so in other words, if the width of the column is 20 inches, the distance between the bars is 6/10 of 20 inches.
That's correct. So in other words, you got your bars, you got your full column, right? You take off the cover on each side, you take off the spiral on each side, or the tie on each side, plus half the bar diameter on each side, and that gives you this distance, right? If you divide that by the total width, that's how you find your gamma. Okay? Now this is for the case when gamma is 0.6. The figure below is when gamma is 0.75. Okay? So if your actual gamma turns out between the two, what you do is an interpolation. Okay, you just approximate. Now, the way these figures work is that on the horizontal axis, you're plotting the moment divided by AG times H, where AG is the cross-sectional area of the column.